Okay, so we're getting to the final phase of the course now. We've got 3 lectures to go. You've got your last homework. So the last homework is on stuff that we've already done up to this point. So you don't need any more of the lecture material for that. For the last 3 lectures, I'm going to a little bit change the style in that what we're going to do more is look at some quite considerable worked examples that are useful in places where category theory is useful in mathematics. Although I'm just going to be a little bit touching on the surface in that I can't fully develop the usefulness, but to give you, I'll be able to give you a flavour to some extent of the sort of category theoretic structures that are used. And together with these worked examples, I'm going to introduce you to some new general category theory that's needed to make sense of the worked examples. So I know what I'm going to do this week and the week after the new year. I'm not completely sure what I'm going to do in the very last lecture. But this week, what we're going to do is the notion of simplicial set, which is something that's very useful in topology and also has important connections with what's called higher dimensional category theory, which is a current very active area of research. After the new year, the first lecture after the new year, we're going to look at something completely different from this course, and then we're going to look at some category theoretic structures that are useful in analysis, looking at complex analysis. So it's going to be a completely different direction for the course in that lecture. And then in the as I say, the last lecture, 2 weeks after the new year, I'm not sure what I'm going to do at the moment. Okay, so did I start recording? Yeah. Right. So the main worked example today is simplicial sets. These are rather easy to define, given what we've already done in the course, but a little bit more tricky to get one's head around. So to understand how to think about it. Anyway, so to define them, we're going to use what's called the simplicial category. And this is normally written as a bold delta, so I shall underline the delta. It's a bit like an eject button, but in any case, we'll use that notation. So the simplicial category has as objects certain sets, which I'll write as square brackets n, and this is the set. So this is non-standard notation in mathematics. Often one uses the square brackets n to be the set of numbers from 0 to n-1. So it's a canonical n element set. But actually I'm using it for a canonical n+1 element set. So a little bit of caution there. n+1 elements. And the maps from n to n are simply increasing functions, order preserving functions. So order preserving functions. Here we're preserving not the strict order, but the non-strict order. Okay, so it's actually a very simple definition of a small category. Here, these are natural numbers. The objects are in one-to-one correspondence with the natural numbers. It's like non-empty finite sets, if you like, with an order on them. Morphisms preserve the order. And the category of simplicial sets, you normally write it, sorry, that's a small s. So S set is simply the functor category from delta op to set. Or another way of saying it is the Presheaves category of delta. So the category Presheaves of delta. So this is called the category of simplicial sets. it looks like a rather arbitrary definition. What it's good for is that such a thing, such a simplicial set, it's a presheaf. That's a family of sets indexed by the objects here, so indexed by numbers with some functions between them, some certain order-preserving functions between them. And you can view these presheaves, this family of sets with these functions, as a kind of combinatorial structure that gives you some sort of combinatorial presentation of a topological space or another mathematical structure associated with the notion of simplicities. And that's what simplicial sets are used for in mathematics. For those of you who know some topology that's involving abstract notions of simplices, there's also a notion of simplicial complex, which is another kind of combinatorial structure associated with simplices for representing a space. Simplicial sets and simplicial complexes are not exactly the same thing, but they serve much the same purpose. Simplicial sets have this nice point that they have a very straightforward definition in terms of category theory concepts. Okay, but just from this definition, it doesn't look like it's got anything to do with simplicities. So let's make a connection with simplices. And we're going to do that by looking at firstly, we want to look at objects of this category. It's a presheaf category, so we've got some canonical objects, namely the representable presheaves. So let's look at the representable presheaves. There's one for each natural number n, because the objects are given by natural numbers n. So the representable presheaf is called the standard, for n, is called the standard n-simplex. So the standard n-simplex. And I'm going to write this as delta superscript n, and this is defined to be representable presheaf, so we apply the Yoneda to the object n, or equivalently, that's the contravariant functor given from the maps so into the Hom functor into n. So this is from delta up to set. And this is called the standard n-simplex. Still doesn't look like a simplex, it's just a piece of mathematics. To explain how it works, let's do an example, but first I'll introduce some notation. So in notation, we're going to write delta superscript n, that's the standard n-simplex, subscript m for the standard n-simplex evaluated at the object n. So in other words, so this is defined to be delta n applied to m, which is by definition just the set of order-preserving functions from the canonical n+1 element set into the canonical n+1 element set. So again, it's just like notation at the moment, but let me explain to you how to think about this, and then we'll look at an example. So we think of delta n as kind of, so this wavy line means think of it like this, as the m simplices inside the n-simplex. Inside the n-simplex. Okay, so I'm not even sure that everybody knows what a simplex is here, but we're going to address that now. Hands up if you do know what a simplex is. Okay, right, good. Everybody does know what doesn't know what a simplex is. That's something. So how does this work? Well, let's have a look at a simple example. We'll take n equals 3. And as you've all put your hand up that you know what simplices are, that's the plural of simplex. So a simplex is like a generalized higher dimensional triangle or tetrahedron or something. So the 0 simplex is a point. The 1 simplex is a line segment, an edge. 2 simplex is a triangle. A 3 simplex is a tetrahedron. A 4 simplex is a 4-dimensional tetrahedron. And as it gets hard to draw, let's just deal with the 3 simplex. So example, the standard 3 simplex. So that's tetrahedron, triangular pyramid, if you like. It looks like that. So the idea is, this is going to be delta sub 3, the 3 simplex. And if we look, what we're going to do is go up the numbers and look at what delta superscript 3 sub n is for counting up from 0, 1, 2, and so on. So delta superscript delta 3, the tetrahedron 0, is, well, it's functions from 0 to 3, which is from the 1 element set to the 4 element set. So there are 4 such elements. And this has 4 elements. And these are the vertices. And that's what you'd expect, because we're looking at, as I said, by the intuition, delta superscript n subscript m is like the m simplices in the n simplex. So here we're looking at the 0 simplices, the points inside the n simplex. We're only in this combinatorial version of the simplex. We're not interested in all the topological points. We're looking at the combinatorics of it. So we're interested in sort of the points, the edges, and the faces. So we're looking at the 4 corners of the simplex. And now if you look at delta 3, 1, well, this actually has 10 elements. You can work it out as the order preserving functions from the 2 element set to the 4 element, from 0 and 1 to 0, 1, 2, 3. But it has 6 important elements. It has 6 non-degenerate elements. So non-degenerate here means given by an injective function.
Can the other 4 elements be thought of as line segments from a point to itself?
The other 4 are exactly line segments from a point to itself. So non-degenerate is injective. So the idea is these 6 non-degenerate elements are, we're looking at embeddings of the 2 element set in the set of vertices, essentially the 4 element set of vertices. Any such embedding of 2 element sets is going to pick out 2 points, and what we get is the edge between those 2 points. We've also got the functions that identify these 2 points, and then we have a degenerate edge, which is just like the 0 distant edge from the point to itself. So the important ones are the non-degenerate elements, and these are the 6 edges. And if we look at 0, 3, sorry, delta 3, 2, so this is the one-dimensional simplices, the edges inside the three-dimensional simplex. We're now looking at the two-dimensional simplices, the triangles, namely the faces inside the three-dimensional simplex. And again, you can work out if you've got the three-element set 0, 1, 2, and the order functions, the order preserving functions into three-element set 0. So the four-element set 0, 1, 2, 3, and you can see that there are exactly 4 of those. So this has, again, 4 non-degenerate elements. Now there are quite a lot of degenerate elements, so I'm not going to bother to count them, because there are quite a lot of ways of identifying points if you're mapping 3 elements into a 4-element set. So anyway, you have non-degenerate elements in the 4 faces. We look at the 3 simplices in the 3 simplex. There's only one of them. So this has, which the identity function is the only order preserving injective function. So it has one non-degenerate element. Degenerate element. So that's the whole tetrahedron. And if we go further up, we have no non-degenerate elements, but plenty of degenerate elements. So 3M has 0 non-degenerate elements. If M is greater than N. Okay, so that's how the standard simplex arises. So why are we using order preserving functions here? Well, the order preservation makes the combinatorics work. It means that because of the order preservation, we only get each face once, namely because you can only list its vertices in one order. So that way we're eliminating, we're sort of imposing by imposing an order on it, we break a symmetry, but in doing so, we're eliminating the need to identify lots of different, sort of n plus 1 factorial or whatever it is, different ways of looking at the same object. And you can see also this definition then, the non-degenerate elements in delta n sub m here. So you always have n plus 1 choose m plus 1 of them. So you can forget these numbers using binomial coefficient, I think. I hope so anyway. I didn't double check that. It seems obvious to me, but I haven't actually double checked it. Right, okay. So that's the combinatorial simplex as encoded as a simplicial set, but simplicial sets also allow us to encode sort of topological objects in terms of sort of more with a topological structure. So we're going to have a look at a different way of encoding a simplex as a topological set, namely the topological way of obtaining a simplex as a topological set. And to do that, we're first going to define the topological simplices. So a topological simplex of dimension n is the usual n-simplex, the usual, so it will be a triangle, topological triangle in the case that n equals 2, and a topological tetrahedron in the case that n equals 3. And in general, we can define this as delta n, so we now use a subscript. There's lots of overuse of the delta notation here. So delta n is going to be a topological space, and delta n is defined to be the topological n-simplex, where a nice definition of this is an n-simplex is determined by all the points inside it, given in what's called barycentric coordinates, in which every point is a convex combination of the vertices. So for the 3 simplex, you have 4 vertices, and a complex combination is a linear combination of them with non-negative coefficients, all of which add up to 1. So we're going to represent the n-simplex via n+1 numbers, x0 up to xn. So this is they're all going to be positive, and they're all going, sorry, non-negative, and they're all going to add up to 1. So that's going to be so they're all between 0 and 1, such that the sum of those numbers is 1. So this is a topological space as a subspace of Euclidean space in n+1 dimensions. So this is the standard topological n-simplex. And actually, this definition gives us a functor. Which I'm also going to call delta, not underlined and with no subscript or superscript, is a functor. This function, delta, that maps n to its topological n-simplex, is a functor from delta, from the category delta, the simplicial category, to top covariant functor. And we need to say it's a functor, so I'm defining it here on objects. We need to say how it behaves on maps. The easiest way to define it on maps is, well, we've got the vertices of the n-simplex. There are n+1 vertices given by sticking a 1 in the relevant coordinates and making all the other coordinates 0. So we're viewing every point as I said, as a convex combination of the vertices. So the vertices themselves have a 1 in one coordinate, and you simply the function from we've got a function from n to m. The corresponding function from delta n to delta m simply is the unique affine function that maps the corners in the appropriate way according to the function from n to m. It's written out in the notes, but I don't think I need to really write it down here. It's sort of obvious you're mapping the numbers, the corners of the n-simplex, and you simply map the corners according to the function, the function f from the action on maps from n to m. You map the corners, and then there's a unique affine function that sort of fills in what it does on the rest of the. I can fill that out in the break if you want to. So we've got this functor from that maps any number to the topological n-simplex, and using that, we see that any topological space gives rise to a natural simplicial complex. Or maybe I'll go to the other board. We're given a topological space T, we can define a simplicial complex, sorry, a simplicial set which I'll call S of T in the following way. So S of T at n is a set of continuous functions, so namely the morphisms in category of topological spaces from the standard topological n-simplex. So the topological n-simplex into T. Oops, I just need a comma there because this is the Hom set. So it's kind of all ways of embedding an n-simplex in T by a continuous function, although the word embedding there is wrong because these functions don't need to be injective. So it's all ways of continuously mapping the simplex n into T. Okay? And this is called S of T. S of T is called the singular something, total singular complex. I don't know if anyone's familiar with this area of mathematics. I'm not very familiar with it, so I don't actually really know the reason for this terminology. I think singular here is referring to the fact that we're not only including the embeddings here, we're also, so if you were looking at ways of embedding the simplex, then, well, then you wouldn't get a simplicial set out, but so in order to get a simplicial set out, it's important that we're not just looking at all ways of embedding the simplex in T, but just all ways of mapping the simplex into T. So it's rather a large simplicial set in general, because you have lots and lots of continuous functions. Why does it define a simplicial set? I mean, I'm given the definition on objects here that the simplicial well, in fact, what I've given so far, I haven't even given us the simplicial set, because I've just given us, for the number n, I've given us the set that's associated to it. We need to show that this is functorial in order to get a Presheaves, but that's actually immediate, because we can simply, we want to define S of T as a Presheaves. We notice that what we've done here is essentially we obtain a Presheaves because this is simply a Hom functor. We're applying the delta functor here, so much like in the first exercise, we've got the object T, and this is now clearly a contravariant functor. We're applying delta, which takes us, remember, the delta functor here goes from our simplicial category to topological spaces, and now the way I've written this makes it clear that this is a contravariant functor from the simplicial category to the category of topological spaces. It moreover makes it clear, because the T here is occurring on the right-hand side of the Hom set, it's clear that there's a covariant functor there, because the Hom set is covariant in the right-hand set. So this defines the above defines a functor S, total singular complex functor that takes us from any topological space into a simplicial set. So topological spaces can be viewed as simplicial sets. Doing so, you completely change the maps. In topological spaces, you have continuous maps. In simplicial sets, you have natural transformations that don't relate in an easy way to continuous maps. I mean, there's a functor, but there's no better correspondence. But it turns out that one does get a very good correspondence when one starts identifying up to homotopy. So, and I'm not going to go into the homotopy here because that's a whole extra direction of, that's the whole extra layer of things to add on top. But just say this is the basis for then a deeper correspondence that arises by also considering a notion of homotopy equivalence in simplicial sets. And then it turns out that actually simplicial sets up to homotopy are equivalent up to homotopy to topological spaces up to homotopy. So then one gets a very nice correspondence. But anyway, this is the sort of the functor that one of the functors that underpins this. But for today, we can just view this from the point of view of for any topological space, we get this simplicial set, namely by looking at how we can continuously map simplices into the topological space. And what I want to end with on this sort of worked example for the moment, but we're going to come back to simplicial sets at the end of the lecture. Simplicial sets that are going to motivate the abstract material we're going to go through, because we're going to address a particular question, which I'm now going to state the question. But then at the end of the lecture, we'll come back to simplicial sets and see a different application of simplicial sets that's not to topology, but rather to higher dimensional category theory, which I shall present just, I'll just present a smattering of that. But anyway, the question I want to use now to motivate what I'm going to do abstractly for the next part of the lecture is to say, well, we've got this connection between topological spaces and simplicial sets. Any topological space can be viewed as a simplicial set. But is there any way of going back? So they're not the same notion until one puts homotopy on top, but not doing that. Is there in any case a way of sort of converting a simplicial set to a topological space? And the answer is yes. And that's by something called the geometric realisation functor. There is a geometric realisation functor that converts any simplicial set to topological space. And this enjoys three important properties, all three of which characterize it. So we're going to give three different characterizations of this functor G. So the first one is G is a co-limit preserving functor such that it makes the following diagram commute. We consider first functor I defined, sorry, not the first functor I defined, but this is the functor that maps the simplex to the n-simplex to its standard topological simplex. So that was this functor here on this board. So then, of course, we've got simplicial set of Presheaves over delta over the simplicial set. So we've got the Yoneda functor from delta to simplicial sets. And in fact, the geometric realization makes this diagram commute only because it's a diagram of functors. It's not appropriate to ask for it to compute up to equality. One can kind of force it to if one wants to, but the mathematically tasteful thing is to just ask for these functors to be naturally isomorphic. So G is a co-limit preserving functor with this property. And what's nice is this gives us the intuition for what G is doing. Every simplex itself is getting mapped to the standard topological simplex. A simplicial set is giving us combinatorial information. Every delta superscript n subscript, sorry, a simplicial set X, let's say, has a set Xn for any n. We view that as the set of n-simplices within X. So X is a sort of structure, and the simplicial set X says X of n is the set given by the Presheaves, and you think of it as the set of n-simplices within the structure we've got. And then the maps between, so the Presheaves structure, the maps between these sets tell us when we're mapping. So the maps are like maps on vertices when we're embedding like lines in, we're mapping one set of vertices to another set of vertices and perhaps identifying some vertices and perhaps not. And that's like embedding, and if it's from M to N, mapping an M simplex into an N simplex. And these maps are telling us which of the simplices we're identifying when we glue them together in certain ways. And the fact that this map makes this diagram commute. It says it maps the simplices in the way that you want, and then it obeys, for any simplicial set here, it obeys the instructions, if you like, in the simplicial set about how the different simplices of different dimensions are glued together along their edges and vertices. Because it's co-limit preserving, it's essentially building this topological space from standard simplices by gluing them together according to the recipe in the simplicial set. So this diagram is essentially saying that. And because of that way of thinking, actually the image of this diagram is always a very nice topological space obtained by gluing simplices together, something called a CW complex in topology. It doesn't matter, we can still view it as going into the category of topological spaces. So G is a co-limit preserving functor with this property that motivates what it's doing. It's kind of gluing together simplices according to the instructions in a simplicial set. That doesn't tell us why G exists, so to speak. I mean, this characterizes G, as it turns out. But it exists because we can construct it explicitly as the left Kahn extension, as something called the left Kahn extension of this functor along the functor y. Doesn't matter what that is for the moment. I'm going to tell you in the next, for the left Kahn in the next part. The left Kahn extension of delta along the Yoneda functor. So we're kind of extending this function in a canonical way to get this functor. It actually enjoys an even better property. It's something called a pointwise left Kahn extension. I won't write that on the board. And thirdly, it's characterized as that G, this geometric realization, is actually left adjoint to this functor S that we defined just here. So the total singular complex functor. So the S functor was from topological spaces to simplicial sets. So actually this total singular complex functor can actually view it the other way around as this geometric realization, when we've got it, is very natural because it's interpreting the simplicial set as gluing simplices together. And then it's nice that we obtain this total singular complex functor from the natural, although harder to define, the natural geometric realization functor via an adjoint. Anyway, so we've got these three properties, and the general part of the next part of the lecture is going to be to elaborate what these three properties, well, you know what the third one means, it's an adjunction, but we're going to look at this, at these two properties. And then if time permits, I'm going to come back to this other application of simplicial sets. So we're going to do an abstract bit in the second hour and then come back and be a bit more concrete again and look at the relationship between simplicial sets and categories. Okay, I mean, it's a bit early, but the camera seems to have gone a bit weird, but anyway, never mind. It's a bit early, but I think it's a good break. Well, it's actually not really early. Let's have a break anyway, so I'll pause the camera. Okay, so I want to, we had this existence of this geometric realization functor, and I gave you three different characterizations of it. I want to say something about why this functor exists and why it satisfies those characterizations, mainly focusing on the first point, I think, because that's the important, that for me is the more important one. So that the existence of this co-limit preserving functor that extends the standard topological simplex functor. But the technology we're going to use is general to any category of Presheaves, so I'm going to do it at that level of generality. And the first thing I'm going to introduce you to is a little useful definition, I think, due to Grothendieck, which is called the category of elements of a Presheave. Category of elements of a Presheave P. So P is a Presheave over some small category C. And the usual notation for a category of elements is to use an integral sign with a P there. Sometimes people stick a C, either superscript or subscript, I don't remember which, so I won't. I mean, so integrals are like sums in some sense, and sums are sort of like collecting everything together. And here we're collecting all the elements of a Presheave together in a single category. There's probably a deeper mathematical reason for the notation, but that heuristic explanation is the best I can give. So the category of elements has as objects elements of the Presheave. But what is an element of the Presheave? Well, an element of the Presheave is an element of P of X for some object X of C. So to give the information, we need to specify an object X of C and an element, which I'll call also little x, belonging to P of X. So here, X is an object of C and X is an element of P of X. Remember, P is a contravariant functor from C to set, so P of X is a set. And morphisms, let's just say maps from an object XX to an object YY. Well, these are simply going to be maps from X to Y in the category C. So these are maps X, F to Y in C that preserve the element. Well, what does preserve the element mean? Well, a Presheave, P is a contravariant functor from C to sets. So P of F will give us a functor from P of Y, the set P of Y to the set P of X. So preserving the elements has to mean that that function maps what little y to little x. So it's such that P of f. To say that's a function from P of y to P of the object y to P of the object x. That maps y, the element little y, to the element little x. And that's it. And we just observe, because objects of the category of elements include an object of C, and the maps are maps between the objects. There's an obvious forgetful functor, is a forgetful functor. U from the category of elements of P to the small category C that we started with. Okay. And the reason for introducing this is the following theorem, which is a nice result. It says that, let's see how I've written it. Every presheaf P contravariant functors from P to that is the co-limit in presheaves of C of the diagram, it's the vertex of the co-limit of the diagram that we get by taking the category of elements as the diagram shape and mapping this along the forgetful functor. That's giving us a diagram in C, and further taking that along the Yoneda functor into presheaves of C. So this is giving us a diagram in presheaves of C of the shape of the category of elements of P.
So we interpret the category of elements as a graph. Just
yeah, we interpret it. So any category is a graph.
Yeah.
I mean, you can define limits for categories. It's the same as the definition for a graph. Yeah. So this is often paraphrased as every presheaf is a co-limit of representables, meaning of some diagram between representables, because the vertices of this diagram, every vertex here is getting, we're going through the Yoneda, so every vertex is being labeled with a representable in the diagram. And this theorem has a name. It's often called the co-Yoneda lemma. Although it's not the only lemma that is called the co-Yoneda lemma. So when people talk about the co-Yoneda lemma, they sometimes mean this, but they sometimes mean other things. It's also, from this formulation, it's not at all clear why it should be a co-Yoneda lemma. It's not at all clear in what sense it is dual to the Yoneda lemma. It can be reformulated using a notion known as coends, and then this statement becomes a formula in coends that if you turn those coends into ends and you dualize the statement appropriately to something called ends, becomes that dual statement is exactly the Yoneda lemma. So that's a motivation for calling it the co-Yoneda lemma, but we can't understand that without introducing concepts that I'm not going to introduce. But nonetheless, we can still call this the co-Yoneda lemma. Right. So, as I might have said a few minutes ago, there's a very long proof in the notes for something, but it's not this. So I do want to give you a feeling for why this works. So I'm going to give you a proof outline. It's not a difficult result. And so proof outline. So we want to show that P is a co-limit for a certain diagram. So we want to exhibit P as the vertex of the cone of the co-cone for that diagram. So the co-limiting cone it's a cone, sorry, co-cone. So it's a co-cone for diagram. That's the kind of cones we have co-limits. So it's going to be indexed by objects of the category of elements, because that's our diagram. And for each such element, we need to have a map in Presheaves of C from the vertex interpreting from the object in Presheaves of C that's been assigned to this vertex of the graph. And that's simply going along the forgetful. So capital X, little x gets mapped to the object capital X, and then we go along the Yoneda here. So we're looking at maps in Presheaves of C from, but we need to give a map in Presheaves of C from the Yoneda of X. Let me put, I didn't put it in the notes, but it needs to be a natural transformation because it's a map in the Presheaves of C into P. And let's call these, let's call the natural transformation here, little c x, comma x. Okay. So this is given by Cx x needs to be a map from the Yoneda of X into P, a natural transformation from the Yoneda of X into P. The Yoneda lemma tells us that those things are exactly in one-to-one correspondence with elements of X, elements of P of X. And little x is an element of P of X. So we can simply define C of X of X, we'll define it to be, what do I call it? Psi subscript object X of little x, where psi subscript X here is the bijection from P of X to actual transformations from the Yoneda of X to P. So this is the one-to-one correspondence given by the Yoneda lemma. By the Yoneda lemma. Okay, so that's the co-cone that we need. So we need to prove the universal property. So suppose we've got any other co-cone. So given any other co-cone, but that's going to again be some maps from the Yoneda of X. What do I call it here? D, indexed by the vertices of the graph, which are the objects of the common category, into some object Q, which is a co-cone. We need to define so given any other co-cone, we want P to be the co-limit. So we need to define the unique natural transformation from P to Q that's going to be a map of co-cones. So the unique natural transformation let's see what I call it in my notes. E. Q that is a cocone morphism. It's given by so this is a natural transformation in the category of Presheaves. So we want to give a family of maps indexed by objects of the category C. And we need to go from then P of X to Q of X. And to do this, we map an element little x P of X gets mapped to if we consider cocone D, where is it? D of X of little x, D of capital X of little x, is a natural transformation from the Yoneda of X into Q, and by the Yoneda lemma again, such things are in one-to-one correspondence with elements of Q of X. So we simply need to, again, apply the Yoneda lemma correspondence. We're using the Yoneda correspondence. So let's stick a P on here. This was the correspondence between elements P of X and natural transformations from the representable for X into P. Psi superscript Q is the correspondence between elements of Q of X and natural transformations from the representable for X into Q. Here we've got a natural transformation from the representable of X into Q. So we simply apply psi of Q its inverse to D in this map dx of X, and that gives us an element of Q of X. So what's really nice about this is the way the Yoneda lemma fits together with the category of elements to get so that this definition works. One still needs to verify that this is a natural transformation, that it's a morphism of cocones, and that it's the unique morphism of cocones that it is in fact the unique morphism of cocones. But this construction gives you the intuition of why the result is true. Okay. Yes?
I don't understand. How is the domain of this function P of X?
So little x here is an element of P of X. Once we've got an element of P of X, so this is a capital, so x comma little x is an element of the category of Presheaves. So we have the component dx of little x, which is a natural transformation. I mean, maybe I've made a mistake, but natural transformation from X to Q. Natural transformation, sorry, from the Yoneda of X to Q. Natural transformations from the Yoneda of X to Q are in one-to-one correspondence with elements of Q of X. So using that correspondence, we get an element of Q of X. Does that explain it, or is it missing?
Yeah, little x, and yeah, was from the category of.
So this is from the category of elements. Yeah. Okay. Okay. Right, so that's nice. At least I think it's nice. Every Presheaf is a co-limit of representable Presheaves. So the representable Presheaves are very sort of significant in the category of Presheaves because all Presheaves can be built out of them. There's a slightly more general perspective on this, which is useful, for which it's, in order to get it, we need just to slightly tweak our definition of the category of elements. It's going to be the same category, but we're going to realize that we can view it in a different way. So I'm going to do one of these things where I modify a definition that we've already got. So this is the category of elements of the presheaf P. But we could write this differently because our objects of the form an object of C together with an element of the presheaf at that object of C. But the elements of the presheaf by the Yoneda lemma are in one-to-one correspondence with natural transformations from the representable for X into P. So instead of putting an X here, we can replace this with an alpha. A natural transformation is the same thing because by the Yoneda lemma, we're now, it looks like we're making things more complicated. Well, so now alpha is a natural transformation from the Yoneda of X into P. Let me just check I used alpha in the notes. Yeah, I did. And now our maps, we can just, again, use the Yoneda lemma to reformulate this. Our maps now from an object X together with an alpha, which is in one-to-one correspondence with the elements of X, of P of X, to an element to Y with a natural transformation beta, one-to-one correspondence with the elements of P of Y. These are now just rephrasing exactly what we had before, but using these natural transformations. These are now maps F from X to Y, such that a diagram commutes, which is that if we go from Y of X to Y of Y, the Yoneda functor is covariant. So we have Y of F, and here we have alpha X. And hang on. Sorry, here we have alpha. This is a diagram of natural transformations. I'm not putting the double arrows in, but we have alpha and beta. Okay. So this is equivalent to the comma category. Sorry, this is equivalent to the category of elements. And this construction is called the comma category construction. This is the comma category. Y down arrow P. So it's just a way, in this particular example, it's just a way of reformulating. So why is the Yoneda lemma here? It's just a way of reformulating the category of elements. But the advantage of it is that this is a construction that makes sense for any functor and any object in the codomain category. So in general, given a functor F between two categories C to D and an object, do I call it Z in my notes or Y? Z in the category D. The comma category F down arrow Z. It's like one of these constructions, like a slice category. It's a general category theoretic construction where now it has objects pairs X and let's just see what I call it in my notes again, X and G, where X is an object of C and G is a map from F of X to Z in D. And the maps from XG to YH are maps from maps X to Y in C such that the same diagram we had before commutes. So apply F, we apply the functor capital F to the morphism little f, then this triangle commutes. Z, G, H. Okay, so you can see this general construction works for any functor and any object in the codomain category. And in the case that this functor is the Yoneda functor and that we've got a Presheaves here, then this is exactly the common category we had here, which is the same as the category of elements. And in general, we have a forgetful. So we have a forgetful functor U, which goes from the common category into C. So it's kind of generalizing the slice category in that if you make this the identity functor, this is exactly the slice category. But it's like a slice category where you're slicing the category C by an object not in the category C itself, but in some category that you're mapping C into, kind of. And the reason for this general formulation is that it allows us to make this definition. Given such a functor F and an object Z in the category of D, we always have a diagram of the following form determined by F, by Z rather, and F. So from the common category of F over Z, as one said, we go along the forgetful to C and along a functor F into B. So this is a diagram in D. So let me call this diagram A. And this diagram always has a cocone. This is a diagram in D, and the object Z is always a cocone for this diagram. So this has, so with a canonical cocone, with vertex Z. Now this cocone is it's indexed by elements of the common category, that's by objects X of C. So these are the vertices of our graph for our diagram. So it's indexed by elements of the common category, and for any such element, we're mapping the vertex in the diagram is labeled by, well, we forget the little g, and that's the forgetful, and then we apply f to it, so it's labeled by the object f of x. So we have f of x here in the diagram. We want a cocone from that, so we want a family of maps indexed by xg into the object z, but g is actually giving us just the map into z. This is giving us the family of maps into z, and it's easy to see that's a cocone for the diagram. And a functor f is said to be dense f is said to be dense if, so this is the definition, if for every z in C, sorry, in D, for every object z in D, z in D, let's call it so the diagram is A and the cocone is B. For every Z in D, B is a co-limit cocone for the diagram A. So it may seem a bit technical, but the intuition is the following, that the functor is dense if every object, so where is it, the functor here? So this, this should be the curly C. So our functor is from C to D. It's dense if essentially every object Z in the codomain category arises as a co-limit of objects of the form f of something. But it's not just an arbitrary co-limit, it's a particular co-limit, namely the one whose diagram is given by the comma category, okay? So every object Z of D is exhibited canonically as a co-limit, in a canonical way, as a co-limit of objects of the form f of C. And having said this, we can now reformulate the co-Yoneda lemma. It's simply saying, I mean, we've basically just rewritten what we had before. It's simply saying that the Yoneda functor is dense. Every Presheaves is a canonical co-limit of representables. So the co-Yoneda lemma, as we're calling it, reformulation, Yoneda functor from C to Presheaves of C is dense. Okay. So what we've done here is we've elaborated so far the way in which, with two slightly different views on it, one using the category of elements, one using the comma category, which amount to the same thing, the way in which every Presheave is a co-limit of representables. The really stunning thing is that every Presheave isn't just a co-limit of representables, but the category of Presheaves is itself can be viewed as being defined by completing the category C with co-limits. So every Presheave is going to be the co-limit of representables. We complete the category C by adding all co-limits in a free way, as freely as possible. So not imposing any more constraints on them other than their co-limits. And this is the main result today that the notes have a very long proof of, because I'm not going to give the proof, I'm just going to give the statement of the lecture. So for something like this, where I don't do the proof in the lecture, the proof is not examinable this is just for the oral exam, it's not examinable, so it is for your edification only. If you're curious as to why this holds, then you can have a look, or you can have a look at a textbook as well. I don't know what will be easier. Almost certainly a textbook. Doesn't have my handwriting. Not that that's the only issue, probably, but anyway, so the main theorem. So theorem, let C be small. That's a small category. Let A be co-complete. And for the, I'm going to say and locally small, though I didn't have a clear enough head when I was preparing the notes to realize whether this, to come to a firm decision as to whether this is absolutely needed. Probably not. But in any case, you know, when our examples are always going to be locally small. Let f from C to A be arbitrary. An arbitrary functor, obviously. So then there exists a co-limit preserving, a unique co-limit preserving functor which I'm going to call F overline from the category of Presheaves of C to A, such that the following diagram commutes. So we've got category C, we've got Presheaves of C, we've got our functor, our arbitrary functor F, that goes from the category C into the co-complete category. So remember, co-complete means has all co-limits. The co-complete category A. We've got our, let's put the hook there because it's, remember, it's a full and faithful functor. We've got our Yoneda functor here. And what there is there's a unique co-limit preserving functor F over line that makes this diagram commute, except once again it's a diagram of functors, and it wouldn't be true to say there's a unique one actually making this diagram commute. You can make the diagram commute, but such things are very artificial, and in any case you still don't get a unique function. At least I think you can, but I mean MacLean actually bothers to do this in some places when sort of mathematically there's no need to, I think. Maybe not in this particular instance. But anyway, the natural thing to ask for is for there to be a natural isomorphism between the two, this functor and its composite here. And then the existence statement is unique up to isomorphism of functors, or up to natural isomorphism. But I'm formulating it like this because you basically see that Presheaves are like a free algebra construction. We're freely adding co-limits. So it has the same property that one expects of a free algebra construction. If you look at any other algebra, so in that case, that's a category with co-limits, then for any functor into that category, or for any map into that category, which in this case is a functor, there's a unique homomorphism. So our structure is co-limit, so homomorphism means co-limit preserving functor that makes the diagram commute. Only now commuting means up to natural isomorphism. Okay, so it's a lovely result. To prove it, one needs to introduce the notion, well, one doesn't need to, but the natural way to do it is to introduce this notion of left Kahn extension, which would have been part of the lecture had there been time, but there isn't. So then one shows that under these circumstances, such functors always have left Kahn extensions. And the left Kahn extension in this case does the job because it turns out to be a functor that has a right adjoint. That's why it preserves the co-limits. And the right adjoint, when you instantiate this, in the case of C being the simplicial category, Presheaves of C are then simplicial sets, and A, which is a co-complete category, topological spaces, and F is the standard topological simplex functor that we had. Then this left Kahn extension, this is exactly what we wanted. We wanted this. We wanted this this co-limit preserving functor that makes the diagram commute. We wanted it to be the left adjoint. That's part of the proof of this theorem, that it's actually a left adjoint to that functor, and it's also given as a left Kahn extension, which are beautiful things, but we don't have time for in today's lecture. Because what I want to do in today's lecture is now, this is enough maybe abstract material, and I want to go back to more concrete things and look again at simplicial sets and consider one more example of a simplicial set that is not at all geometric in nature. It's combinatorial, but it's related to categories. And this is something called the nerve of a category. So it's interesting because it's another example of a simplicial set. So we sort of view it as a collection, any simplicial set X at n, we view as a sort of structure that has some abstract notion of n-dimensional simplices in it, and the set of X at n is the n-dimensional simplices in that structure. And this particular one we're going to look at is something called the nerve of a category. So for any small category C, its nerve, n of C, is the simplicial set so remember, the simplicial set, so that's n of C is going to be a simplicial set, so that's a functor, a contravariant functor from the simplicial category into sets, defined by well, let's just, so we want to define a functor from the simplicial category to sets. So we map n, the n+1 element set, from numbers from 0 to n, gets mapped to composable sequences of morphisms in C of length n. So there are n morphisms which needs n+1 objects between them. So it's composable sequences of n morphisms in C. So namely, such a thing looks like an object x1 together with a map f0, sorry, an object x0 together with a map f0 that goes into x1, to a map with a map f1 that goes into x2, and so on. And then we end up getting, at the end, go all the way through to x sub n, because we need n+1 objects to have n maps between them, and the last map will be f of n-1. And the action on morphisms is contravariant. Let me just make it consistent with my notes. So I have a very non-deterministic thought process that decides on the names of things. So the problem is when I run the same process twice, even within the space of a few hours from the last time I ran it, I get a different answer unless I check what I got last time. So anyway, we're going to have a contravariant functor, so we consider an order-preserving functor from 0 up to n here into 0 up to m, and we need to map that to, it's a contravariant functor, so we need to map any, well, unfortunately, I can't just take, I'm going to depart from my notes, so I can put that, call that n and that m, and then we can simply take this sequence here, which is an element of the nerve of C at n, and this gets mapped to, so just to say writing, so this gets mapped to, we now need a sequence of length of m+1 objects. So here we simply we take f of 0, x of f of 0, we go to x of f of 1, and we go to here, and at the end we have x of f of m. So here we're selecting out, not quite a subsequence, because f might also identify some points here. So we've got we're going through, we've got m+1 collections. We've got a sequence of n+1 objects taken in order where we might take the same object a few times. And the maps between them, I won't write it down, are simply you compose all the maps in between. And if you stay in the same place, you stick the identity in. So it's kind of the obvious thing to do. So with adjacent compositions, let's write it like that. as maps. The amazing thing is actually this nerve, and I don't want to clear a board, so let's use a different color and stick it in this corner. I haven't defined it in this way, but in the notes it's in more detail. But N actually defines a functor from the category of categories into simplicial sets. So here I've defined it for an individual category, but actually it gives us a functor. There's a natural way of extending this to a functor from the category of categories into simplicial sets. And moreover, this functor is full and faithful. And this says, in some sense, that we have a way of viewing categories as simplicial sets, and we don't lose any information. The functors between them are also just correspond to maps of simplicial sets. There's a question about what to do about natural transformations, but let's not go in that direction. I mean, natural transformations in an appropriate sense do make sense here. But the point is, categories can be viewed as special simplicial sets in a way that you don't lose any information. And actually, this observation is crucial to modern generalizations of the notion of category. So there are some modern notions of high dimensional category, namely things called quasi-categories, or infinity one categories is another word for them, that have becoming very important in mathematics now, and they were developed to a considerable extent by Jacob Lurie in a major book he wrote in the first decade of the 20th century, towards the end of it, called Higher Topos Theory. And the crucial idea there is to view these generalizations of categories as simplicial sets where ordinary categories are included, because they can view an ordinary category as a simplicial set via its nerve, but these generalized higher dimensional categories are also included as special simplicial sets. So, I mean, that's a whole very advanced topic in itself, so we won't go into that, but I just wanted to make the connection. All right. Sorry, I'm very slightly overrun. Anyway, that's it. So I'm going to stop the video.